Okay, hi. Good afternoon and good night, everyone. Thanks today for joining us for today's session, SAM 3D, Powerful 3D Reconstruction for Physical World Image. I'm Yuanhan Zhang, and we have a packed agenda today exploring how the segment anything philosophy is evolving from 2D pixels to 3D space. Here is how we will spend our time. The first 30 minutes, Weiyao Wang will present SAM 3D, focusing on general object reconstruction and break the data barrier for the physical world. And next 30 minutes, Xitong Yang will take the floor to discuss SAM's 3D body, deep diving into human mesh recovery and new momentum human rig. And the final 10 to 15 minutes, we will open the floor for the joint Q&A session with both speakers. And our first speaker is Weiyao Wang, is a research engineer at Meta Superintelligence, and he is a core contributor to SAM3D and has extensive experience in 3D reasoning and multimodality learning. Our second speaker is Xitong Yang, is a research scientist at Meta Superintelligence who earned his PhD from the University of Maryland. He's an expert in fine-grained video understanding and the lead behind the SAM's 3D body model. And to keep the discussion organized during the final Q&A session, we ask that you to use the raise your hand feature in the meeting control. I will call on you individually and unmute your microphones so you can ask your questions directly to our presenters. Okay, without further delay, let's get started. Weiyao, the floor is yours.
Um, hey, thanks, Yuhan, for doing the intro. Hey, everyone. Thanks for joining. I'm Weiyao together with me, our Xitong and Jiawei, who are all from the SAM 3D team. And today we're very excited to talk about SAM 3D. So, point of clarification first. The SAM family has released like 4 models last year, all the way from SAM 3, SAM 3D objects, SAM 3D body, and SAM audio. Today, we're going to mainly cover SAM 3D, with me starting to talk about SAM 3D objects. So to begin with, what is SAM 3D? SAM 3D tackles the problem of what we call visually grounded 3D reconstruction. Okay, what do I mean exactly by that? So when a camera takes a picture, there's a three-dimensional world outside, and this three-dimensional world gets projected to the camera. This process is basically computer perception, how computer represents the visual world. SAM 3D's goal is to reverse this perspective transform and recover the objects in 3D, including the part that weren't visible in the original image. It's basically undoing the computer perception process. So why does this matter, right? Consider applications in embodied intelligence, robotics, AR, VR, which employ vision to understand one's surrounding, the 3D world, the physical world. By some definitions, the fundamental purpose of this visual perception is to know what is around us and where they are. So I would argue that this task is one of the central problems to computer vision. Let's do an example here. Here, SAM3D takes a single RGB image as an input. With the segmentation mask on the right, you see, to tell what the objects the model needs to reconstruct, the model can output a full 3D scene with texture and pose and shape. This can either be represented as a mesh or 3D Gaussian splat that looks really nice on the right. So this is basically SAM3D. How do we really make this work? Well, we feel there are 3 key insights that we'll go through and share today. To begin with, SAM3D basically reframed the 3D reconstruction problem, pushing 3D reconstruction beyond the synthetic setting towards a more real-world 3D perception. The second part, which is a major barrier before, that basically prevents 3D from achieving what it can do with SAM3D is the data barrier. There is a scarcity of 3D data that needs, and we overcome this by design and build a large data annotation engine. And finally, the data engine will need to be tightly coupled with a redesigned training paradigm for 3D. We adopt the modern LLM training paradigm and apply that to 3D. We'll dive each of these three items, and this will be the structure of this talk. When you think about 3D generations, right, like people typically really often focus what we saw on the left, which are basically the asset generation models. They take either a single view or multiple views and reconstruct a single object. Well, as you noticed in the introduction, we moved away from this paradigm to focus what we define as the 3D visual grounding to ground the generation in the 3D. So now you have this full scene 3D reconstruction on the right. Since the 2D to 3D problem by nature is lossy, right? You don't really have visibility to the parts that are not visible in the camera. We believe to solve this problem, a generative approach makes the most sense. And we use a generative model, a rectified conditional full matching model. This basically jointly diffuse the shape, the pose, and the texture given the image and the object prompt, which is typically a mask we take here. We split this task into two parts. The first is more on the geometry side that do dense geometry prediction for both the layout, where is the object and the shape. And then we take this coarse geometry and leverage, because the geometry itself, once predicted, is pretty sparse. We leverage this and perform texture and refinement prediction on top of it. We would like to cite the work called Trellis, which largely inspired our architecture design. So now we formulate the problem and we provide the architecture. The question is then, where do we get the data? 3D has a very famously data scale problem. If you look at the scale from text to image to 3D is actually very, very small. Like the magnitude is much, much smaller for public data set compared to images or text. But things can be much, much worse. I'll come to the small dots in the next few slides. So the vast majority of the available 3D data primarily consists of standalone single 3D objects. This is what, to remind what we call the asset generation data. But if the goal is to actually construct a real world 3D, this is far from enough. Prior work, they use to solve this problem by rendering like this 3D assets back to 2D and solve this reverse rendering problem. While this is valuable, this setup, the objects are often centered in the image, they don't have any background, and they're often unoccluded, which is far from what the real world looks like. Training on such data, while they led to impressive results, they were mostly what you saw on the right. Again, this is just asset generation. You can't really get the full 3D reconstruction that we saw from SAM3D. So we need to push beyond what we call this canonical view of objects as input and train on this. So to generalize to real world, what we actually need is the natural scenes that you have partial view of the object being occluded, low resolution, small objects. And this is a problem because we don't have that much data. And this really real world objects is what we believe are missing. So this is the dot here. Even though the isolated canonical view assets, we have about million scale data, we only have about 10K scale data of the real world reconstruction paired with the image. So this is still a big data barrier that we believe. So let's collect some data. What we do is that we basically build a data annotation pipeline that breaks up the data collection into a few subtasks. The annotator will begin by select the interesting object and annotate the mask on them. Then we generate the shape and texture from our model suite, and the annotator will pick the best one based on their perception. So human get involved in picking which one is the best. And after that, the pose will get aligned based on the 3D scene reconstruction. So we collect the pose at the last. This sounds really trivial and easy, right? But the problem is that to get this 3D shape is pretty difficult. If you think about not doing this selection-based algorithm, asking humans like myself included to annotate like such 3D shape will be very, very difficult. So a key insight here is that you can move from, asset creation from human to asset verification. So the human only need to pick the best ones like rejection sampling. And then as a result, we'll be able to collect this like data in the real world. You can see like these are pretty challenging and different from what you saw before with the asset gen style of images. And even on the right, for some of the cases where the model keep, not being able to generate like high quality results, we loop them into 3D artists. But this is actually a very small scale collection. And we want to use it to the most difficult case. And this is good for data efficiency, for example. So with the data engine right now, we're able to scale collect more data, but this isn't enough. This needs to be tightly coupled with the training paradigm. The overall philosophy for the training paradigm is don't try to teach the model all at once. Let's build capabilities in stages. The first stage is pre-training, which is basically similar to the asset generation process. I know I said like we need to move beyond that, but this offers a larger scale of data available and is very good for pre-training purposes. We show the model again the key and canonical renderings and ask it to reconstruct the shape and texture from those. This gives the model the basic capability, how to go from an image to a coherent 3D object. But a model trained only on this data cannot really handle natural image. We can't emphasize it enough. It doesn't understand complex lighting. It doesn't understand how to handle occlusion. And it doesn't know where to place the object. You will just have the standalone assets. You won't have the full 3D scene. So to unlock those missing capabilities, we introduce two more stages beyond what most 3D pipelines do today, a mid-training stage and a post-training stage. The mid-training is where the model learns what we call like street smarts of the real world. These are three core capabilities here. The first is we believe post-estimation. The model needs to learn where to place this object, like in the scene. The second is occlusion robustness. The real images are pretty messy, like you can see things blocking each other. A model must reconstruct well, even though if the object is only partially visible. And finally, object prompt following, like this is still like an object-based model. So the model needs to know, like I need to reconstruct this specific object that user wants. So to teach this capability, we build a special data set, which we call render pasted object. This is what you saw on the right. We take an isolated 3D object, render it from a random viewpoint, and paste it onto the natural image background. You see, this looks a little bit funny. You can see like this basket this thing there like is on a tree. Like it's not exactly what the real world looks like, but it gives the model just exactly the contextual information it needs to learn about pose and knows how to follow object mask and learn to handle occlusions. And after mid-training, the model now has this capability, but we still need to teach how to behave on real-world image and produce what human would prefer. And there's what the post-training kicks in. These stages use the full data engine we just discussed, which is fully real-world images. We run the model on natural image. It produces multiple candidate 3D reconstructions. Human pick which one is the best. It's like a kind of 3D human in the loop feedback, like RLHF. And then we fine-tune the model so it outputs what's aligned with the human preferences. This alignment step is actually pretty important. It's what turns a capable but raw model after mid-training into something that is very predictable, stable, and give consistently good results on difficult, challenging real images. Now, if we step back a little bit, if this feels familiar, it is familiar. It's basically the LLM recipe applied to 3D. In pre-training, an LLM learns to predict the next token. In our case, we teach the model how to reverse render a clean canonical view back into shape and texture. Then in mid-training, LLMs learn domain-specific knowledge like coding, math, or medical reasoning. Sense3D is doing something very similar here. The model will learn how to handle occlusion, how to place object, and how to follow mask properly. And then in post-training, this is where LLMs get the magic dust, like alignment, RLHF, or instruction following. Sam3D also gets this through alignment. It learns to behave the way actually the model learns actually, how to behave what the human prefers and produce the shape and texture that human like. And now this is the exciting part. Once you have this pipeline, as what LLM does, you can just run the data engine and post-training in a loop. It's like a flywheel. The model helps generate, candidate 3D prediction, human pick the best. The model trains on the best ones, so the model gets better. And now you redeploy this model back to, collect more data with better annotations and tackle a more difficult case in the data collection process. This cycle can repeat, every few weeks. This is what we do. And over time, the model's prediction are increasingly preferred. As you can see, the elo score keeps getting better every 3 weeks by doing this hill climbing. So now we talk about the 3 key insights. Now I will try to convince you that this is a good model. How well does SAM3D do? We compare against, existing methods. You can see that SAM3D tends to produce much more complete geometry. On the left, this is the visual examples. And we highlight here, there's the 3D artist results, which is like the human upper bound. We can say SAM3D is pretty close and sometimes even have more details than what the artist can generate. And when we run an actual quantitative, human preference test, SAM3D is overwhelmingly preferred than all the public baseline available. So at the object level, things are looking pretty solid. For people who like texture, we show more examples here. We can see the results like in fly around, which we reconstruct the full object with texture. We show this were not really cherry-picked. We show both the good cases and some cases where the texture is wishy-washy, not great. But this is how the model performed. Of course, I'm sure at this point people have seen, the demo stuff like those. If you see try it, the quality looks roughly like this. But we believe objects are just the beginning as we try to convince we need to reformulate the problem to actually solve something really useful and do the full 3D scene. So we also do a scene level evaluation. The qualitative gap is pretty clear on the left compared to baselines. And again, human raters overwhelmingly prefer what SAM3D gives against all the baselines. At this point, you've seen the ideas, you've seen the metrics, you've seen human preference tests. Now the best way to understand is to just try it. As I mentioned, there's an online demo on the segment anything playground. Click on object and literally watch it appear in the 3D as what you can see on the right. It's very satisfying for the researchers like me. And honestly, it feels even a little bit magical. Still, I play it after a few months after we release the model. I want to show a couple of fun examples to close this conversation. These are examples we tried while building this. We run SAM3D on the famous painting, like the death of Socrates. And the result is kind of surreal to us. You get this almost immersive 3D scene lifted directly out of the 2D painting. It's definitely not a use case we trained for. We don't have this type of data during collection. But it's so pleasing to show how strong the model becomes. Even further, one of our researchers really liked this one. The model shows very, very good generalization to even something like a sketch like this. Obviously, there's no 3D ground truths because they just don't exist. We also saw a few twists with similar example where someone just draws a sketch or do a car design components, and the objects pop out with SAM3D, which is kind of magical to us. Before we wrap up, we'll talk a little bit. This is often a common ask when people talk to us. It's what's the install? What's next after SAM3D? We believe SAM3D is just a beginning. It doesn't really finish the line with 3D research. To truly recreate a world, there are 4 places where I think we could push further. Precision. As we show also the result, as you play with the demo, we can see we should get better texture, more exact geometry, maybe more sharper details. And pose sometimes is a bit off. We want to get better, basically. This is basically closing the remaining gap in the 3D visually grounded generation task we described. We want to go for motion. At New Riffs, we heard there are a few works already doing SAM4D. This is a very good direction, I believe. We want to go in from single image to handling videos, adding time, doing 4D reconstruction, or maybe even understand the dynamics, understanding like how things move and how things deform. And this will bring naturally to us to a very ambitious but impactful research direction, which is physics. We want to understand how objects interact, how they can support each other, how they might move, make future prediction. Especially if we want to bring this to robotic use case, this is very critical. And going for local, right? Now, this is all about scaling things up. We want to do more objects, maybe larger things, or taking multiple frames. So maybe one day we can reconstruct the city from just a few views. These are big challenges, but we feel this is super exciting. Finally, I can't emphasize enough. Like none of this would be possible without the amazing team behind here. Like we got like Jiawei here as well. If any of this work, resonates with you, like shoot us an email, contact us. We're always happy to answer questions. Or alternatively, if you are really mad at us for some specific reasons, just file something on GitHub and the team will take a look at this. Thanks so much for coming. Oh, by the way, we're also hiring summer interns. If you feel you're a good candidate or you know somebody who's a good fit, contact me, Xitong, or Jiawei. We always want the best talents. Again, thanks for listening. I think I'm done with my slides.
Okay, cool. Yeah. As we all mentioned, so Sam3D body is like a totally different model from Sam3D object. So here we are develop a model for full body human mesh recovery. So to get started, I will just share a short video. Here is sample from our demo website showing what the task is. Basically, given an image of a human, our model will predict the human body pose. It includes the body key points, and also the hand. So you can also see the hand pose in these examples. And it also works for like multiple person in the image, and they also predict their relative location in the image. So this is our Sam3D body model. So human mesh recovery is it's a kind of a fundamental research problem for computer vision. So in the past 10 or 20 years, there's many methods developed in this field. So there are two basic questions here. First is how do we represent the human pose and shape? So one of the direction is to represent using a parametric model. So basically represent the body in a low dimensional and compact representation. So there is some pretty well-known work here, Simple is widely used in academia. And then the second question is that how do we estimate those human parameters from monocular images? So there are also different directions. One is learning or regression based. Basically, you can train a neural network to directly estimate those human parameters. And you can also do optimization to just do the mesh fitting to get the human parameters. Or there are some hybrid methods. So even though recent work has made significant progress on this field, we do see there are many common failures, like if there's hard poses or the process is occluded in a scene or captured from uncommon viewpoints, the model usually fails. So here are just examples from one of the recent model, multi-HMR. Also, many of the recent model, they cannot do body pose estimation and also fine-grained hand and feet pose estimation at the same time in one model. So our Sam3D body would like to tackle these two problems. So the general pipeline of human mesh recovery looks like this. Given an image, we'll train the parameter estimation model, and then to get the pose and shape parameters, and then we fit to this parametric human model to get the mesh. So our Sam3D body model basically is a promptable regression model. So it's a fit-for model to get these pose parameters. And we do full body mesh recovery, as we mentioned, we do body and feet. And we also based on a new mesh parameter, we call it momentum human rig. I will mention it later. So in this talk, I will go to some details about I think two top two like things that leads to the Sam3D body success. The first is the data engine we built. How do we get the high quality 3D annotation from like large scale data? And the second is how we designed our like promptable model to give us both body and hand pose estimation. I will cover the data part first. So what makes a good training data for human pose estimation? So when we look at the common data set used for like HMR training, we do notice that there are pretty limited high quality 3D annotations, especially for in the wild images. So there are like synthetic data set like BATLAM, there are like also large scale in the wild data set, but you cannot get like both high quality 3D ground truth and in the wild images at the same time in most cases. The second challenge is that many of the images doesn't include like challenging poses or like these uncommon viewpoints. That makes the model like less robust or cannot generalize well to those like scenarios. So that's our like principle to design our data engine. We would like to include images from diverse image source. Like we have synthetic data, we have lab captured data. We also have like lots of multi-view data set that we do mesh fitting on. And for sure, we also have in the wild images from like SA1B data set. And we also have a like mesh fitting pipeline that it's model in the loop, meaning that we have like the latest model to help us get better mesh fitting quality. I will go into details later. And we also have like a image mining and post mining pipeline that we use vision language model to help us to find the most interesting images and pose to do the annotation. So yeah, as I mentioned, we want to get high quality mesh fitting from different image sources. So the first category is like multi-view mesh fit, multi-view images. The data can come from like Eagle XO40, Harmony 40. There's many of these like open public data sets we can leverage. And on these multi-view data sets, we can definitely like leverage the spatial like multi-view consistency and also temporal cues to get like high quality mesh fitting results. And we also like collect data from like SA1B and also some other common data set like AI Challenger and COCO to do this single image mesh fitting. And we have a pipeline to get high quality annotation. I will show you in the next slides. So this is also pretty important because all these images are in the wild. So it can help our model to generalize to this scenario. The last is that we also have some like scan-based mesh fitting. So we have like synthetic data, or we have like some dome capture data, which have like just ground truth mesh scans, and then we can get the fitting from that. So here is our like data engine pipeline in high level. The first step is to do like image or pose mining. Basically, we have like a simple vision language model. We provide some prompt and to let the model to find the image of interest. So basically, we care about like diverse images and also image with hard poses and occlusion, etc. After we get those images, we'll do some filtering, and we also have like manual annotation of 2D key points for these in the wild images. So with these images, we'll run our own dense key point detector to get a pretty dense like key point detection on the surface of the people here. So basically, we have like roughly almost 600 dense 2D key points on this human. They can be used as like supervision signal when we do the mesh fitting. And the dense key point detector is conditioned on the sparse 2D key points we got from the manual annotation. So we can get like pretty accurate dense key point detection here. For the mesh fitting, so we have the dense key point from the detector. We also have the initialization of the human body like pose parameter from our own Sam3D body model. And then we run the optimization to get fitting results. So the whole loop can be done like multiple times. I think we did it like twice or 3 times to get the final like mesh fitting results. So yeah, this is the training data we use for our model. I think it's also in our like technical report. So we have like over 7 million images paired with the 3D annotation. And we also have like some data that is used for like hand pose training as well. So this including like body and hand pose estimation. So this is the data side. And I'm gonna cover the model side. So I think some highlight of our model is that it is like a promptable design. And it also have like 2 dedicated decoders for both like for body and hand pose estimation. And we also use a new parametric model as we mentioned. So the new parametric model we call it like momentum human rig is a technology developed by Meta and also used in many of Meta's products. I think one like key property here is that it couples the skeleton pose and also the body shape. So it can provide like richer control and better interpretability for the full body reconstruction. So you can check out this new rig on the GitHub. So it's also open source in Apache 2.0 license. So here is like a high-level architecture of our model. Basically, we adopt the encoder-decoder like transformer encoder-decoder architecture. It's pretty standard. Some like new designs here is that our model will condition on some additional prompts to get the pose estimation output. For example, we can condition to the key points, or we condition on segmentation mask and camera intrinsic camera parameters. So the model also condition on some like we call it auxiliary key point tokens. So in experiments, we have observed that conditioning on this like learnable, even though it's just learnable key point tokens, it can help to improve the 2D alignment on the images. And as shown in the figure, we also have a dedicated like hand decoder, which can be used to estimate like more accurate hand pose estimation. I will show some examples in the future slides. So here is overview of our performance for sure. Yeah, I think we get the state of our performance on both like 2D and also 3D estimation like benchmarks. And we also did like human preference tests, like, and our model achieved is much more favorable compared with all the existing methods. Here is one example how we show to the users to compare the results of 2 models. And the model the users will compare both the 3D estimation results and also the 2D alignment results and pick the better one. Here's another example. The left is our SAM 3D body model, and on the right is NL. And we also do some ablation on the key point and mask prompt we provide to the model. So on the left, I'm just showing that like by providing more key point prompts, 1 or 2 during inference, the model performance can definitely improve. For example, like on Coco, the PCK is the percentage of correctly detected key points will significantly improve if we provide like key point prompts to the model. On the on the figure, you can see the key point prompt can be something like the key points on the shoulder or the key point on the hips. So on the right is a table to ablate the impact of the mask condition inference. On the data set that with like human occlusion, like HI40 and Harmony 40, and we also have a subset from SA1B we call like multi-person. So condition on a mask, the inference result will give like much better reconstruction if we have the mask as condition. And the last part I would like to show is that in addition to the body pose estimation, we also got state-of-the-art performance on hand pose. So here's some results on the free hand data set. So in addition to like comparing to some whole body methods, we also achieve like comparable performance compared with some hand specialized method like wheeler and hammer. And on the right is some visualization on our hand decoder branch, the estimation results of our hand decoder branch. So here is a little bit more details about our like unified hand decoder. So when we do the inference, our model will first, given the body crop, we'll first predict the full body pose estimation results, and we can also estimate the hand location. And then for each of the hand, we'll crop the hand to get like higher resolution input to the model, and then we can estimate the hand pose again. After these two results, we can combine them by merging the parameters so that they can combine to a full body parameter. And we also leverage our like key point prompting capability to prompt the elbow from the body decoder and also wrist from the hand decoder, so the model can have both accurate hand wrist location and also body location. So these are some visualization. Without the hand decoder, you can see in some like challenging hard poses, the model fails to predict the hand pose correctly. And without a key point prompting, sometimes the wrist location can be off because the hand decoder and body decoder can predict like slightly different location of the wrist. By combining everything together, both the key point prompting and also the hand decoder output, we can get more accurate wrist location, more accurate elbow location, and also more accurate hand poses. So here is just some visualization. This is some test case we use internally. It's one of our intern. So this is just to showcase that we can, so even though our model is an image-based model, we can generate like consistent full body pose estimation results, including the body and also hands. Here's another example. Okay, I think that's all from my side. So for some future work, for sure, I think we are just an image-based model. So definitely the next step for the extension can be like to support video, to get like more temporally smooth results and also even get like global trajectory in the work coordinate, not just camera coordinate. And another direction we can think of is to support human object interaction. So currently the Sense 3D body is just a human model, and probably Sense 3D objects focus on just lifting objects. It's pretty interesting to combine and do a better job in human object interaction. And another direction could be like to better handle different viewpoint. For example, like for eagle view images, Sense 3D body may fail because the only like part of the body parts is visible. Yeah, so thanks for listening. I think that's my part.
Okay, thank you for this wonderful presentation, and we actually know a lot. And next is our QA session, and if you have any question, please don't mind to raise your hands. Use the raise your hand feature in the meeting control, and I will call on you individually and ask you to unmute, and you can ask any question you want.